Welcome to the video for part 3 of module 1, which covers linear inequalities in one variable. Friendly reminder to be completing your guided notes as you go through this video. So we've talked about equations already, and an equation is a statement that two quantities are equal. An inequality is a statement that two quantities are not equal, or you could kind of think of it as unequal. So there are multiple inequality symbols. You could see an equal sign with a slash through it. That means is not equal to. That's the least common, but I wanted to show it to you anyways. We've got less than, greater than. We've got less than or equal to, meaning it could be one or the other. Like 6 is less than or equal to 8, but 6 is also less than or equal to 6. One of the two has to be true. Greater than or equal to, so for example, 3 is greater than or equal to -1, but -1 is also greater than or equal to -1. These two examples right here are the or equal to part. So something to think about as you're solving these equations. So let's complete these inequalities. So I've got 2 compared to 6. There's a couple inequality symbols I could put there. I could put 2 as less than 6, or I could do 2 is less than or equal to 6. Both would be true. I have -5 compared to -10. Well, one is bigger than the other. -5, even though it's negative, is still greater because it's less far from 0. So I would have -5 is greater than -10, or -5 is greater than or equal to -10. Both would work. Here I have 6 and -9. -9, that's far to the left on our number line. So here I have 6 is greater than -9, but it also could be greater than or equal to. Your call. You get to choose. So let's work through some examples. So let's translate these phrases into an expression, an equation, or an inequality. So the difference between a number and 9. Well, remember, difference is a word for subtraction. So we could do the difference between a number and 9. It's going to be the difference between x minus 9, where x is our number, because it's my favorite variable to choose. 3 less than a number is 14. So if I have a number and I take away 3, I get 14. A number is increased by the product of 6 and a number. So here I have a number is increased, so added by the product of 6 and a number. 5 times the sum of a number and 2 is less than 15. So I have 5 times the sum means add, of a number and 2 is less than 15. That gives us an inequality. And then I have the quotient of 5 and a number is at most 10. So it could be less than 10, but it also could be equal to -10. So it's less than or equal to -10. When we solve an inequality, what we're doing is we're finding the set of numbers that make an inequality true about a statement. Whereas when we were solving equations, and I had something like x equals 2, and 2 is the only solution, if I have an inequality like x is less than 2, there are tons, if not, there are infinitely many, really, values x could take on. Here, x could be 0, it could be 1, it could be -7, it could be -2/3, right? I can't list them all, there's so many. So what we're doing is we're finding the solution set. It's going to be a set of numbers, and we're going to talk about 2 ways to represent those, in set notation and interval notation. We also say that these numbers satisfy our inequality. So for set builder notation, what a set is a set is a collection of things, in our case, numbers. So here's an example of set builder notation. So here I would have the set of, using these 2 brackets, those mean the set of all numbers x, so all values of x, such that, this vertical bar means such that, in this case, x is greater than 0. This says the set of all numbers such that x is greater than 0. In other words, any value greater than 0. You'll always need brackets, a variable, the vertical bar meaning such that, and the characteristic that's being met. So x is greater than 0. In our previous example, I said x was less than 2. So for that example, in set notation, since I can't write out every single number when x is 2, that would take the rest of my life, plus some, I can write the set of all numbers, x, which is our variable, such that x is less than 2. And this just tells me any number as long as x is less than 2. I also like to visualize my inequalities on a number line. So here I have x is less than 5. Since 5 isn't part of my solution, I'm not really going to graph it, but I'm going to draw an open dot because 5's not included, but every number really close to less than 5 is. So like 4.9, 4.5, those would all be included. And since it's everything less than 5, I'm going to shade the side of the number line where it's less than 5. So this would be a graph of my solution set, but I could also write it in set builder notation. So it's all values of x such that x is less than 5. Here, I have x is greater than or equal to -3. So -3 could be in my answer because it makes this inequality a true statement. And since it's greater than, it's going to be the bigger numbers. We're going to shade this to the right. So what I have in blue here is my solution set graphed. And I could write it as in set builder notation. I've got x such that x is greater than or equal to -3. So another way to write it is in interval notation. So for interval notation, we use square brackets to indicate endpoints that are solutions. So those are for less than or equal to and greater than or equal to. We use parentheses to represent endpoints that are not solutions. So for less than and greater than. And I've got a couple examples. I've got all numbers less than 0. So that would be x is less than 0. We could graph that on a number line. And let me do that real quick. Here's 0. Changing color. All numbers less than 0 would be everything to the left. So I write that in interval notation. Negative infinity is over here. And because we don't know where infinity is, it always gets a parentheses. So I read my number line from left to right, just like we read in English. And I would have negative infinity with a parentheses to 0. That comma tells me negative infinity to 0, and then another parentheses. If I have all numbers greater than or equal to 4, I could write that as x is greater than or equal to 4. I could also graph that. These are my very lazy number lines, so sorry. So 4 is included. That gets a closed dot because 4 would make this a true statement because it's greater than or equal to. And I shade to the right. So again, reading my number line from left to right, I hit 4 first. And since 4 is in my solution, it gets a bracket. And then I go all the way to infinity. So in order to solve linear inequalities, we treat them pretty similar to equations, but not exactly. So we still need to simplify our algebraic expression on each side. We can use the addition property and the property of multiplication to get our variable terms on one side and the constants on the other. The difference is I have to flip the inequality symbol if I divide by 0. So if I multiply or divide by 0, I have to flip the sign. So let's look at an example. Let's say I have 2 is greater than -3. And I, using the property of multiplication, could multiply both sides by -1, and that's supposed to remain a true statement, right? I can multiply both sides, and this should keep its inequality property. Well, now I have -2 is greater than a +3. This is a false statement. So I have to flip the sign. We have to flip. So this becomes -2 is less than 3. Then it maintains its inequality. We can express our solution set in interval notation and graph our solution set on a number line. So let's practice some examples. So here I have x minus 7 is greater than negative 12. I'm going to add 7 to both sides. I have x is greater than negative 5. So I can put this on my number line, negative 5, 6, negative 4, right? I don't have to fill the whole thing in. We can see what my solution is going to be. I graph negative 5 with an open dot because it's greater than, so it's not included. Greater than means I shade to the right. So my solution set is everything from negative 5 to positive infinity. So in interval notation, negative 5 gets a parentheses because it's an open dot, all the way to infinity, which also will get a parentheses. In example 2, I have 6 minus 2x is greater than or equal to 18. I'm going to subtract 6 from both sides. Negative 2x is greater than or equal to 12. I'm going to divide both sides by negative 2. Because I'm dividing by a negative, I have to flip. Don't forget to flip your sign. So I have x now is less than or equal to a negative 6. So negative 6, make our number line. Negative 6 is graphed with a closed dot because it's less than or equal to. X is less than or equal to negative 6. I shade everything to the left. That's negative infinity over here. So when writing this out in interval form, I would have from negative infinity to 6, and 6 gets a bracket because the endpoint is included. Our last example, we're going to have to distribute. I have negative 3x minus 12 plus 2 is less than or equal to 7 minus x. Negative 3x minus 10 is less than or equal to 7 minus x. Let me add x to both sides. Negative 2x. Let me add 10 to both sides is less than 17. Ooh, we're going to have a fraction. So I have negative 2x is less than or equal to 17. I divide both sides by negative 2. X is greater than or equal to negative 17 halves. That's negative 8.5 in case you were wondering. And I can still graph this on a number line. So if I have negative 9 and negative 8, it's right in the middle of those two. So here's negative 17 halves. I graph that with a closed dot. And its x is greater than or equal to negative 17 halves, so I shade to the right. And then in order to write this in interval form, even if I'm running out of space, we change colors so you can see it better. I would have from negative 17 halves, but I made a mistake. That shouldn't be a parentheses. That should be a bracket, so we'll fix it. All the way to positive infinity, which always gets a parentheses. When we're solving compound inequalities, what I want you to do is treat the left and the right like you treat the middle. So what I do to one side, I have to do the other. Here, I've got 3 is less than x plus 2 is less than 8. So I need to subtract 2 from the middle. Well, if I do that, in order to maintain the inequality, I also have to subtract it from the left and from the right. So I have 1 is less than x, which is less than 6. How am I going to graph this? I'm so glad you asked. So my endpoints are 1 and 6. I know x has to be some number between 1 and 6, but 1 and 6 can't be included. So it could be 3, it could be 4, it could be 3 halves. So it's going to be all the numbers in between these two. And in order to write it in interval form, I'm still going to read from left to right. So coming from the left, first thing I do is I see 1, but 1's not included. And then I keep going and I see 6, but 6 not included, so it gets a parentheses. And then I stop because nothing else has been shaded on my number line. This would be our solution set in interval notation. In example 5, we're going to do the same thing. I'm going to add 1 to both sides and the middle. I get -1 is less than -3x, which is less than 6. Now I have to divide everybody, by -3. And because I'm dividing by a negative, I have to flip the signs. Since there's 2 of them, I'm going to flip them both. So I have 1/3 is greater than or equal to x, which is greater than or equal to -2. And this should be a true statement, right? Is 1/3 greater than -2? Correct. Cool. So we remember to flip our signs. All is good. We label our number line. 1/3 is going to be right about here. So 1/3 is included. That gets a closed dot. -2 is included. It gets a closed dot. And x is going to be in between those two. So if I'm writing this in interval form, reading from left to right, I have -2 to 1/3, and both got brackets because both endpoints were included. So we've seen equations that have no solution or infinitely many solutions, and this can also be true for inequalities. So for example, if I have x is greater than x plus 1, and I wanted to solve this, I'd start by maybe combining like terms. So I'd subtract x from both sides. Well, that's going to give me 0 is greater than 1, which is false, right? I got a false statement. That means there's going to be no solutions because there's no number that's greater than itself plus 1. I could also have something that has infinitely many solutions. So in that case, it'd look like x is greater than or equal to x, or x is less than or equal to x, because that's always going to be true. So let's see if that happens. Or it could look like 2 is greater than or equal to 1, right? As long as you get a true statement, or 2 is greater than 1, right? These are examples of true statements you could get. So here I have 3x plus 3 is greater than or equal to 3x plus 1. I subtract 3x from both sides. 3 is greater than or equal to 1. That's always true. That's like super true, which means there would be infinitely many solutions. So you could write from -infinity to +infinity. You could draw a number line and then graph the entire thing. Just color in the entire thing, shade the entire thing. When it comes to false, I wouldn't draw a number line and then leave it blank. I might write that null set symbol, 0 with a line through it. There's no solutions. That would be my recommendation. So let's solve a couple of problems. I have 6x is greater than 2x plus 6. Wow, I can't read. Okay, I have 6x is greater than 2 times 3x plus 6. So we're going to distribute first on that right-hand side. 6x is greater than 6x plus 12, because we have to distribute. I subtract 6x from both sides. I get 0 is greater than 12. This is false. 0 is not greater than 12. So there's going to be no solutions. For our last example in this section, again, we're going to have to distribute. -2x plus 6 is less than -2x plus 8. If I add 2x to both sides, my x's go away. I have 6 is less than 8. That's true. That's always true. So no matter what value of x I plug in, I'm going to get a true statement. My answer is infinitely many solutions, all real numbers. I can write it as an interval from -infinity to infinity. I could do this fancy R, that means all real numbers. That's everything on our real number line. It's up to you. Last, here is a table comparison of set notation and interval notation with the graph, just in case you wanted to see all the possible solution sets that you might encounter in the homework and on quizzes and things like